Ladies and gentlemen, welcome to my presentation with the title Holistic Lifecycle Analysis of Bridge Solutions. My name is Tim Zinke, and within the next minutes I would like to introduce you into a bridge solution which uses steel sheet piles as bridge abutments, as you can see here in the picture. Then I will explain to you what I mean when I talk of holistic life cycle analysis. And finally, I will combine these first two topics into a case study. Everybody of you have already seen steel sheet piles on a building site, and these piles are normally vibrated or drilled with a pile driver like this one in the background into the soil. Normally, these piles are applied as wall for the excavation site, and in these excavation site the abutment can be erected. And then after the usage it is possible to extract the piles, and if it's not possible they are left in the ground. But we cannot use the piles as a wall, we can also use them as a part of an abutment. And in this example here, this is a pedestrian bridge in Denmark, the piles are part of the abutment, but they are not bearing loads. You can see it here on the top. There is no possibility to bring the loads into the sheet pile. If we use the steel sheet piles as a permanent foundation and as a load-bearing component, we can build bridges like this one. And you can see here that on the top of the bridge there is a knife edge connection, it is called, and this connection is able to transfer vertical and horizontal loads as well as fatigue loads into the steel sheet pile. This is the kind of solutions I would like to talk with you about within the next minutes and within our holistic analysis. The knife edge solution, you can see here, is nothing else than a caping beam for the load transmission. It is a reinforced concrete beam, and for example in Germany a general construction technique permit exists. If we have a look at the design, at the reinforcement design of this knife edge connection, you can see here a model. This is a model from ArcelorMittal, where it is shown how the different reinforcement bars have to be placed on the top of the steel sheet pile. And with this construction, as I said, you can transfer all the loads from the superstructure into the substructure. Now I would like to introduce you into the second topic, the holistic assessment. When we perform holistic assessments, we have to do at least two critical definitions. We have to define the spatial and the temporal boundaries. In this picture you can see the spatial boundaries. The first level I will analyze in the case study is the bridge structure itself. This is the brown-gray part you can see here in this picture, and we will assess the erection costs as well as all the costs in the use phase and the dismantling phase of this structure. Beyond the structure itself, you can also include other impacts that, for example, result from the affected routes. The calculation method is called external cost calculation. And within this one I include all the impacts that result from the obstruction of traffic. As an example, when we have the building site underneath the bridge, the cars normally using the highway are affected and they need more time to pass the building site. So I have time losses when I try to pass the building site as a car driver. These time losses can be transferred into external costs by using a monetization. As an example, for 1 hour commuter traffic a monetization rate of 20 euro per hour is applied. A second impact are pollutant emissions that also result from the traffic underneath or over the bridge. And, you know it, we can, for example, transfer CO2 emissions into euro. And this is also done in the external cost calculation. Then, thirdly, I can calculate detours that are necessary if the bridge is closed completely. The second important definition are the temporal boundaries. And in our calculations, we have a look at the complete life cycle, and therefore we also need all the information that are existing within the life cycle. Of course, we start with the production of our different building components, then we assemble them on the construction site, so this is the erection of the bridge, and all these A modules describe the complete erection phase of the bridge. Then, secondly, I have the use stage, and then finally we have the end of life stage where we are dismantling the bridge and we do the waste processing. Furthermore, a module D exists where benefits and loads covering reuse, recovery, recycling and so on are aggregated. And then there's a possibility to also include the external effects. And as I also already described on the slide before, the external effects are the impacts on the traffic, as example resulting from congestion, time losses, air pollutions and so on. The costs in all these life cycle stages are calculated for 4 different groups. The groups are the superstructure and substructure group. Then all the equipment parts are grouped into one group. And then finally we use a group temporal where, for example, site equipment, traffic safety measures and so on are combined. This structure interacts with the traffic when building site measures are performed. The calculation of the case study I will show you on the next slide includes all the life cycle stages here on the slide, all the different groups of the bridge, as well as the external costs resulting from an obstruction of traffic. Beyond the calculations method introduced here, you can also apply a calculation of ecological impacts, a life cycle assessment. We did this in the project, that is the basis for the calculations shown here, but we did not include the ecological impacts into our paper because we did not have enough space. Let's start with our case study. I will use a normal composite bridge shown here in the picture. It is a 2-span bridge with a length of 80 meters of each span. The width of the superstructure is 12.25 meters. And I will use 2 different variants of the abutment design to show the results of the holistic analysis. The variant 1 is a steel sheet pile abutment. The second variant is a reinforced concrete abutment with board piles underneath. When we start with our analysis, the construction schedule is very important to do the traffic calculations and then to calculate the external costs. Here you can see the construction schedule for the steel sheet pile abutment. On the right side you can see how long the different phases last and what kind of traffic routing I use. For example, a 2+2 routing means that for each direction I have 2 lanes which can be used by cars. The second abutment, the reinforced concrete abutment, needs a longer construction period, and this longer construction period is responsible for higher external costs. And when we now compare the erection periods for the abutments, you can see that we have a net saving of 32 working days. So if I speed up my construction period, I can produce benefits for all the vehicles passing my building site. As I already explained, the results of our assessment can be grouped into 3 different cost categories. If I compare the construction costs, I can see that the results differ in the substructure. The steel sheet piling abutment costs 0.28 million euro, while the reinforced concrete abutment costs 0.34 million euro. So the concrete abutment is more expensive and the costs are 18% higher. As a result, my complete erection costs are 8% higher for the reinforced concrete abutment. If I now calculate my life cycle costs, I can see that in the year 0, the erection year, my 8% difference occurs, and then the different life cycle costs nearly develop the same. And at the end, I still have an advantage for my steel sheet piling abutment of nearly 5%. The reason can be found that my steel sheet piling abutment has a corrosion protection system. And this corrosion protection system has to be renewed 2 times within the use stage. And therefore, within the use stage, the sheet piling abutment is a little bit more expensive compared to the reinforced concrete abutment. Finally, we can calculate our external costs, and there the difference of our result is the largest. You have seen that the construction period for the reinforced concrete abutment is much longer than for the steel sheet piling abutment, and therefore the external costs are 27% higher for the erection period. Within the use stage, the obstruction of traffic is the same for both variants, so the external costs are the same for this period of the life cycle. Overall, the external costs for the concrete abutment are 14% higher compared to the steel sheet piling abutment. In our paper, we introduced a second case study which compares 2 different superstructures. If you're curious to find out which design leads to lower life cycle costs and external costs, please have a look at our paper. Finally, I hope that in the future we will see more solutions like the ones shown in the picture here.